Hi friends, in the previous lecture we discussed about finite state machine, how to design finite state machine, and we designed some simple finite state machines. Today we'll be discussing about deterministic finite state machine.
Deterministic finite state machine is defined as m is equals to k summation delta s a, where k is finite set of states, summation is an alphabet, s belongs to k is an initial state or start state, a is a subset of k, which is a set of accepting states, and delta is a transition function from a state and input symbol to the next state. The set of all strings accepted by M form the language defined by the deterministic finite state machine. A configuration of a DFSM M is an element of k into summation star. Configuration captures two things that makes a difference to the machine's future behavior, that is its current state and the input that remains to be read. And the initial configuration of the DFSM M is written as Sm, W, where Sm is the start state of the machine M and W is the input string. Transition function delta defines the DFSM one state at a time. Delta is a set of all pairs of states in M and characters or symbols in summation. Transition function is represented by the current state, the current input symbol or a character going to or leading to the next state or a new state. We often reduce the set delta to those pairs that are useful or to only those that can lead to an accepting state. What do you mean by a complete FSM? A complete FSM has a transition defined for every possible state and every possible character in the alphabet. It can cause FSMs to be larger than necessary, but always processes the entire string. Let us see an example where summation is AB and this is the FSM given. Let us not bother about what all this FSM is about, but this FSM consists of two states Q0 and Q1. According to the definition of complete FSM, from every state there must be one compulsory transition from every for every input symbol. That is, here we have two states. One is Q0 and the other one is Q1. From each state there must be one compulsory transition for input symbol A and B. A and B. So if you see here, from Q0 we have one transition for A and one transition for B. Similarly from Q1, one transition A and one transition B. Hence the FSM is complete. Whereas incomplete FSM is the one which defines a transition for every possible state and every possible character in the alphabet, which can lead to an accepting state. If no transition is defined, then the string is rejected. Let us see an example with summation having A and B. So this is the given FSM. As we discussed, from each state there must be one compulsory transition for every input symbol. That is, state Q0 and state Q1. We have two states, and from Q0 there must be one compulsory transition for input symbol A and B. Similarly, there must be one input symbol transition for A and B. Now, if you see in this DFSM, Q0 has one compulsory transition for A, input symbol A, and one compulsory transition for input symbol B. So this is correct. So this is satisfied. About Q1 doesn't have any transition for A and B. Hence, this FSM is incomplete. The yields in one step relations yield of M is represented as Q, the state, W, the input symbol, yields Q dash comma W dash if and only if W is equals to AW dash for some symbol A from summation, and delta of Q comma A leads to Q dash, and yield star of M is a reflexive transitive closure of yield of M. What do you mean by computation using FSM? A computation by a FSM M is a finite sequence of configurations C0, C1, so on up to Cn for some n greater than or equal to 0, such that C0 is the initial configuration, Cn is of the form q comma epsilon for some state q in K of the machine M. Here epsilon indicates empty string. Entire string is processed and implies a complete DFSM. That is, starts with the initial configuration, yields C1, C1 yields C2 configuration, C2 yields so on up to yields Cn. However, M halts when the last character has been processed or a next transition is not defined. Let us see when the string is accepted or rejected by a DFSM. A DFSM M accepts a string W if and only if starts with the initial state S for the input string W for multiple yields, reaches a state Q where Q is a state in the final states of M after processing the entire string. Similarly, a DFSM M rejects a string W if and only if start with the initial state S for the string W for multiple yields, reaches a state Q where Q does not belong to any of the final states of M. That is, Q is not a final state after processing the entire string. And the language accepted by M is defined as L of M is the set of all strings accepted by M. Till now, we discussed the definition of DFSM, its configuration, transition functions, yield, computations. Now let us design some simple deterministic finite state machines. Let us see an example. The language containing all possible strings of A's and B's, that is alphabet is AB, and the string W contains substring AAB, that is all possible strings will be having a substring AAB into it. Let us see some possible strings in this language. So the possible strings are, the first string can be AAB or AAB followed by A or a B, AAB. So before the substring I can have a or B accepted. AAB, after that I may have some string. Before AAB I can have some string. This string is also must be accepted by this DFSM. Similarly AAB, before AAB and after AAB I may have some substring. So these are the possible strings in this language. And now we are supposed to design a deterministic finite state machine which accepts all these strings of this particular language. So how to design? So there are two steps. First step is satisfy the language. So what are the language states? W containing substring AAB. What is the first string accepted by this particular string of this language to be accepted by DFSM? AAB. String length is 3. Then initially we need 4 states to design a FSM for this string AAB. So let us start designing. This is the initial state 0 going to state 1 with first input symbol A, then from 1 to state 2 second symbol A, and to state 3 for symbol B, reaching the final state. So we got a compulsory substring AAB reaching the final state. Is the DFSM complete? No. Why it is not complete? As we know, the DFSM will be having the transitions such a way that from each state there will be one compulsory transition for each input symbol. So in the second step what we are supposed to do is we have to have those compulsory transitions without violating the language. So let us start with initial state 0. From initial state we have a transition for A going to state 1. What about B? So B, what happens if I take B as a self loop to the same state Q0? What happens? So before AAB I may have any number of B's. Does it violate the language? No, because AAB is a substring. Before that I can have anything. After that also I can have anything. So from state 0, one transition going to state 1 and another transition B going to state 0. So next let us go for state 1. State 1, one compulsory transition to A going to state 2. What about B? Can I take a self loop as I have taken for state 0? What happens? Let us check. If I take a self loop, then what happens? I may have AAB if I don't take this loop. What if I take this loop? A, B, A, B. Now you can see here, this self loop will violate the language. It will not have substring AAB. It will be having A, B, A, B. But we want one compulsory substring AAB in this particular machine. Then this self loop I can't take here. So next what to do? Can I take a transition here? Just see what happens. I'll be having compulsory string A, B. And if at all after this first A, if at all I come across a B, then it must go back and then again it must have a substring A, B. So I hope it's clear now. From state 1, one compulsory transition going to state 2 for input A, and for B it is going to state 0. So state 1 is over. Next come to state 2. In state 2, for B I have a compulsory transition to state 3. What about A? Can I take a self loop? Yes, I can take a self loop. Let us see. What if I take a self loop here? If no self loop, then we have A, B. If we have a self loop, then that will be A, B. Ultimately, we will be having the substring A, B. So state 2 has one transition to A, one transition to B. Coming to state 3. So for state 3, can I take a self loop for both A and B? Yes, I can. Why? Because the language states it must have the substring AAB. I have a substring AAB reaching the final state. After that, I may have any number of A's and B's. Still, this string will be accepted. So, now if you see, the DFSM is complete, which accepts all the strings containing substring A, B. Let us take up another language containing all possible strings of A's and B's ending with substring AAB. Previous DFSM we designed was having a substring AAB, whereas this language has all possible strings ending with substring AAB. So the first possible string in this language is AAB. So to design FSM for this string AAB, we need 4 states. So let us design and as we had done in the previous FSM. State 0, 1, 2, 3. 3 is the final state for the string A, B. So is this DFSM complete? No. We have to complete it such a way that from each state we will be having one compulsory transition for input symbol A and B. So let us start with initial state 0. We have one compulsory transition for A. What about B? Can I take a self loop? Check. Is it possible for me to take a self loop for B? Yes. What it states, if I take self loop before AAB, I can have any number of B's. This self loop does not violate this language. Next, coming to state 1, I have A, compulsory transition. Can I take B as a self loop? Just check. What happens if I take B as a self loop? At that time what happens? A, B, A, B. So it will end with B, A, B. But actually we need, it must end with A, A, B. So this self loop of B violates the language. So I cannot take this self loop here. If I cannot take self loop, then what I must do? Language is having substring AA ending with substring AAB. So if any B's, I must have before the substring AAB. So now you can see, if I have a B, then it will go back and end with a substring AAB. Coming to state 2. State 2, I have a compulsory transition for B. What about A? Take a self loop and check. Can I have a self loop here? What happens if I have a self loop? If I don't take self loop, it will be AAB ending with AAB. If I take the self loop AAB, then also it ends with AAB. So state 2 is satisfied. Then last state 3, we have to have one compulsory transition A and B. What to do? Can I have a self loop for A and B as before? No. Why? Because if I have a self loop, then it will violate the language ending with substring AAB. So I cannot have AAB here. Then what to do? If I have a A, then it must be followed by another AB. So I'll take the transition A here. Now you see A, B. If I have a A, again it must be followed by another A and B reaching the final state. So for A it is over. What about B? If I have a B, then what to do? It must go back to state Q0 and have ending substring AAB. So here completes designing a DFSM for all possible strings of A's and B's ending with substring AAB. The third language, which consists of all possible strings of A's and B's starting with the substring AAB. That is, possible strings in this language are AAB. So first you may have AAB and after that you may have any number of A's and B's. So how to construct DFSM for this language? So first step is The first string in this language is AAB, as we have designed for having a substring ending with AAB. So here also we'll first design for the string A, B reaching the final state 0, 1, 2, 3. So next is we have to satisfy the language and complete the DFSM. Starting with state Q0. Transition A going to state 1. Next is for B. Can I take a self loop? So let us see what happens if I take a self loop. So if I take a self loop, then the string will start with a B, not with AAB. So the self loop will violate this language. So what to do? We can't take self loop. If I take the transition to state 1, now what happens? It must start with AAB, but you will end up with starting with BAB, which violates the language. So this is also not possible. So what if I take this transition to state 2? So what will be the possible string accepted? Starting with initial state 0, BB reaches the final state, whereas BB doesn't belong to this particular language. So this transition also doesn't satisfy. Then last option, let us try that also. From initial state to state 0 to state 3, transition B. What happens here? Suppose to accept a string AAB, but end up with one single B reaching the final state, which violates the language. So transition B from Q0 can neither go as a self loop, nor to state 1, nor to state 2, or to state 3. Then what to do? At that time comes a state called as trap state or dead state or error state, state D, wherein this B transition will be trapped to this state. This state is called as trap state or dead state, as it will be having incoming transitions to it, but it will not have any outgoing transitions to any other states other than the dead state or error state or trap state. So now from state 0, one transition going to, for input symbol A going to state 1, B going to dead state. So going to the next state 1, A we have. What about B? Can I take a self loop? Take a self loop and check. Is it possible? Will it be correct? A B. Instead A B violates this language. So again I cannot take self loop for. So what to do? Go for using the trap state. from one transition B going to dead state. Next, from two transition for input symbol B reaches state 3. What about A? So A also must be again trapped to dead state. State 2 is over. Next, coming to state 3. Can I have a self loop of A and B to state 3? Let us see. Self loop A comma B. Will it be correct? Just check. Starts with A, B, and after that I may have all possible strings of A's and B's. Then having a self loop to the final state is correct according to the language. So state 0 we have balance, state 1 we have two transitions, state 2 we have two transitions, state 3 we have two transitions. Similarly for dead state or error state also we'll have a self loop to balance the transition. So this is the DFSM for all the strings of A's and B's starting with a substring A, B. As we discussed, an error state or a trap state or a dead state is a rejecting state from which the string can never go back to an accepting state. So in this lecture, we discussed the definition of DFSM. We designed three simple DFSMs. We'll discuss some more designs of DFSM in the next lecture. Thank you.